Let's try to solve another exam problem like the one on screen. They said calculate this and write it in this format. Okay, so you know that if you are dividing complex numbers, most important thing, always multiply by a conjugate. So, oh sorry, I just made a mistake. There is 1 plus I. So if you spot any mistake in my videos, don't mind just to comment and tell me where I made a mistake. 1 minus I. We multiplying by a conjugate and we're doing both sides on the numerator and denominator just to keep the value of the problem, not manipulated. And 2 by 1 is going to give us 2. 2 by negative I is going to give us negative 2I. And we're done with 2. 3 by 1 is going to give us plus 3I. And 3I plus, by is going to give us negative 3I squared. Now we're moving to the denominator. Okay, on the conjugate you always say multiply. How do we multiply? You always multiply the first and the first, the last and the last. So because other terms, the middle terms are going to cancel each other anyway. So we're going to have this by this giving us 1, this by that giving us negative I squared. Okay, so we're looking at the top now, working with them like terms. This and this are going to give us I, because one positive I, and we know about I squared, they disappear and change what is in front of them. So we're going to have 3 and that one giving us 5, right? Plus all over in the bottom, this is going to be uh, I squared, we said is going to change to be I squared. I squared, what they do? They said they disappear, change what is in front of them. There's going to be what? Okay, plus 1, and that is going to make it 2. Then we will have 5 over 2 plus 1 over 2I. So reviewing our problem again, we multiplied by a conjugate, and what we did, we just foiled, and you know what, when then we got I squared, and I squared always disappeared, change was in front of them, and it disappeared, change was in front of them, it was minus, and then we got 1 plus 1 giving us 2. So we are 2 over 5 over 2 plus 1 over 2 I. We are written in this format, right? That's what they wanted, so we satisfied the form. We now have another problem on screen. So if you can notice, I'm always doing 2 problems per video, especially on complex numbers, because these 2 problems, there are 2 types, 2 different types, and they always come like that in your exams, always come in 2. So in exam you expect a question like the one that I started with and this one. The first one is always dividing complex numbers, and the second one is always cubing or raising some complex number to some degree, and they always make sure that you lose them. But please make sure that you listen and watch what you're doing on your side so that you make sure that you don't make the same mistake. So this is the complex number that we're given here. So first we need to get the modulus of which is always, let me call this complex number z to work with. So z is going to equal to root of 2 power 2 plus 2 power 2, okay? So forgive me for that. That is going to be 8, or not 8. It's going to be 4 plus 4. Yes, 8. Then that is going to equal to 8 root. Okay, that is your, you just got yourself a modulus for this complex number. Okay, so let's just put it there. Z is equals to root 8. So you know the next thing, you need to get the argument of z. Argument of z is going to equals to tan arctan of the imaginary part, of which is 2, and all over the real part 2, negative 2. Then you are going to get what? That is going to be tan 1, negative 1. Okay, but we know something. We know we have a very let me show you how you always remember your special triangles. One thing about special triangles, root 2, or should I say the root is always on the hypotenuse. Or I mean 2 is always on the hypotenuse. Whatever triangle you want to draw on the special triangle, you always put 2 there. Okay, root 2, and for a 45 one, you always have to have 1 and 1, and then here you have to have root, pi over 4, and you're going to have pi over 4. This is how to remember them. 2 is always on the hypotenuse, and here you have pi over 6, of which is small, and you have pi over 3, of which is almost bigger, and this one is going to take 3, and this one is going to take 1. So this is how I remember them. First of all, 2 is always on the hypotenuse, and then here you put the bigger one gets 3, the small one get 1, and here it's 1 by 1, so no problem. So this one is the same as this one, so it's going to be pi over 4. But you notice that it's negative. If you go back to your plane, here is your plane. Remember, you have the imaginary part, you have the real part here, and we're looking at the negative real part. So negative real part is just here. So here, meaning this pi over 4 is here. Remember, we're working with an angle from here to here. We just got an angle from here to here. From all the half revolution, we know that it's equals to pi. So we're just going to say pi minus 4 pi. Then that is going to give us obviously an argument of 3 over 4 pi. So now we have an argument of z is equals to 3 over 4 pi. So I've cleaned my board. We got the modulus, or the radius. We'll have the argument of z. So we can now plug this thing into a polar form. That's all we need to plug things on polar form. Let me call this complex number z, as I've done before, and it's going to be 8 open brackets cos the argument 3 over 4 pi plus I sine argument 3 over 4 pi close. This is your complex number in polar form. Then if we're in polar form, we can now apply the De Morgan's theorem, right? Remember, if you raise any complex number with some power, it's same as just raising the modulus and multiplying the argument by that power or that index. So we're going to do that just now. Okay, so there is one important formula if you're working with these, and it is if you're working at root of complex numbers, it's theta plus 2k pi multiplied by, let me say, multiplied by n. All this is multiplied by n. Okay, so we are going to do what and our n in this case, we're saying it's cube root is 1 over 3, right? So we're going to have 1 over 3 here. So let me just remove this n and put 1 over 3. 1 over 3. So this is the same as 0, I'm not theta, plus 2k pi all over 3. Okay, we're going to do it first. What if k is 0, right? What if k is 0? If k is 0, all this is going to be 0. We're just going to divide our argument by 3, right? So this is going to be 3 over 4 pi divided by 3. Let me not write it like this. Times 1 over 3, of which is just going to cancel, and you'll have your argument as 1 over 4 pi or quarter pi. Then z, then you're going to write like this, and this one is going to be what? It's going to be raised by a cube. So let me just write it here. It's going to be 8 1 over 2, and outside is going to be 1 over 3. You know the power of this law of exponent that you can just interchange. You can just bring the other one outside and bring the other one inside. So it's going to be 8 and 1 over 3 and put 1 over 4 outside. So 1 over 2, I mean 1 over 2 here. So we just interchange. This doesn't change any value, right? So we're allowed to do it. Okay, so the next thing, we know the cube root of 8 is 2. 2 times 2 is 4 by 2. Then it's another, it's 2 again. So this will turn to 2. This will be 1 over 2. That is same as 2 roots, like this. Okay, so here what we'll have, cos, and then we already have our argument as pi over 4 plus I sine pi over 4. This will happen if k is equals to 0. Let's try if k equals to 1. To make things simpler for us, we just divide theta by 3, of which we have done that. Theta by 3, I think that's how we got our pi over 4. Pi over 4. And the only thing that is changing is this one, because this one's not changing. So now we're looking at what if k is equals to 1. If k is equals to 1, we're going to have 2 pi all over 3, right? And to make things easy for me, what I'm going to do, I'm just going to change which one? Any. I'm going to change multiply, which one? Let's just multiply by 4 over 4 this side. It really doesn't matter which one you took. Remember, this is like this, and here you can now have you can take out a comma, you can take something common here. It's going to be 4. Okay, 4. Oh no, just to make things easy, let me just multiply by 4 over 4 both sides. This side, I know I need to make it the same. I need to make it this side I need to multiply by 3. Okay, that doesn't change anything, so we're going to have 12 here. So bear with me, sorry. Then we're going to have 12 here, and if we have 12 here, we can, how many times 12 go here? It's going to be 1, and then here we're going to be left with what? 3 pi. And how many times 12 goes here? It goes 1 time again, and here we're going to be having what? This is 8 pi, right? Plus 8 pi. Then we can add this one, we end with an argument of 11 pi all over 12. So if k, this was for k equals to 1. If k equals to 1, z1, let me call it z1, is going to be pi 2 open brackets cos. The argument is going to be 11 pi all over 12 plus I sine 11 pi over 12. Okay, let's try it for, what if now k equals to 2. If k equals to 2, this one won't change. This one already divided by 3, I did. It will be pi over 4, and the only thing that will change will be pi plus, and the k will be now, it was 1, it's going to be 2, right? Yeah. So we'll have 4 pi all over 3. Okay, so now we add here, then we do same thing as one that we did. We just make it to be 1 denominator, multiply by 3 over 3, multiply by 4 over 4, and then we're going to have 4 dot 3 here. Okay, these are both here. Okay, then we're going to have 3 pi, these are both here. We're going to have this by this, give me 16 pi. 16 pi plus 3, 3 plus 16 is going to give us 19 pi all over 12. So if k is what? We're looking at k is what? As 2 here. If k is equals to 2, this is going to be our argument. So z2, this one doesn't change. Cos, what is happening here? The argument is going to change to be 19 pi all over 12 plus I sine. The argument is going to be 19 pi all over 12. So we've just got our three roots, right? Because we're supposed to keep root the complex number, and this is our result. So hope you're following. Please subscribe and like, share the video. If you find it interesting, don't forget to put that thumbs up.